I now call to order the lecture portion of the Society's 2515th meeting in the 154th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and the PSW Members Lecture by Carey Lisse. The Society is grateful to PSW Full Year Series sponsors, PSW member Mike Helton and Helton Associates LLC. Thank you, Mike. We're also grateful to the series sponsor, PSW member Joe Schulman. Thank you, Joe. And we are grateful to the sponsor of this lecture, PSW member Andrea Meredith and University of Maryland Baltimore Foundation, Inc. Thank you. The Society needs your support. It actually costs money to stage these lectures and to record them and post them to the website and all the rest of the things that we do that are kind of mostly invisible. And if you are interested in sponsoring a lecture or a series or the annual sponsorship, please see me or Robin Taylor, our executive director, or speak to any of the other members of the general committee who are here. If you've already given, but you would like to give some more, you can do so through the website. And if you haven't given and you want to give some, you can do so through the website, or please see me. I'll be happy to facilitate your donation. Thank you very much. And I thank all the people who have donated to PSW. I'm pleased to announce the following new members. Barbara Illman, retired director of the Institute for Microbial and Biochemical Technology and currently honorary fellow of the Institute for Discovery at the University of Wisconsin-Madison, interested in microbiology, biochemistry, and biophysics, who learned of PSW from Catherine Gebbe some years ago. And Susan Farrell, principal at Susan Farrell Advisory, interested primarily in long-term energy outlooks, including scientific and technology developments impacting the energy sector of the world economy, who learned of PSW from PSW member and former president Bob Hershey. We welcome them both to membership. And I would, of course, add tonight's speaker, Carey, but he is already a member and also a former speaker, so we just welcome anyway. So all members are entitled to a signed copy of Volume 17 of the Bulletin of the Philosophical Society of Washington. If you have not received yours already as a new member, please see me after the lecture, and I will be happy to give you one. Carey will be getting a personally signed copy anyway, so you don't have to see me after the lecture. Please note that all members are invited to receptions and dinners with speakers preceding each lecture, where we often find the most enjoyable camaraderie and interesting discussion. If you're interested in membership, you can access the membership application on the PSW website by going to the home page and clicking the blue Join button at the upper right-hand corner. If you're here in the Powell Auditorium, you can take one of the business cards in the back and use the QR code, or you can talk to any one of us on the general committee, and we will be glad to facilitate your application. The requirements are very straightforward: a genuine interest in science and payment of the $75 annual dues, which hasn't changed in 20 years. Recording Secretary Scott Matthews will now present the minutes of the 2514th meeting and the lecture by Jamie Bach on Spherex. Scott.
Thank you, Larry. Good evening. On April 25th, 2025, members of the Society and their guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2514th meeting of the Society to order at 8:03 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included a lecture by Joshua Semetter titled Unidentified Anomalous Phenomenon: From Sensationalism to Science. The minutes were approved pending a minor correction. President Milstein then introduced the speaker for the evening, James Bach of the Jet Propulsion Laboratory at Caltech. His lecture was titled SphereX, an all-sky infrared spectral survey explorer satellite. The speaker began by saying that SphereX was designed to explore fundamental questions about astrophysics and cosmology. These included the origin of the universe, the history of galaxies, and the origin of water in planetary systems. He said that SphereX will perform the first all-sky spectral survey using a single observing mode with no moving parts. The speaker showed an animation of SphereX, describing many of its unique features, including the large cones, which act as infrared heat shields, the passive radiative cooling, which uses no cryogens or mechanical coolers, the 20-centimeter aperture telescope, the linear variable filters, the mosaic focal plane array, and the LEO spacecraft supporting and aiming the instrument. He said that the telescope is currently operating at below 80 Kelvin and that the focal plane array is below 55 Kelvin. Bach then described how SphereX performs spectroscopic measurements using linear variable filters. A single point in the sky is imaged onto a single point on the focal plane array through one of 6 linear variable filters. As the spacecraft sweeps across a portion of the sky, the point on the focal plane array moves vertically along the array and along the variable axis of the filter. In this way, each of the vertical points on the focal plane array contains intensity information at a particular wavelength. In order to acquire a complete infrared spectrum from below 1 micron to 5 microns, the spacecraft must sweep over the same portion of the sky 3 times, imaging in 2 separate wavelength bands and recording 51 exposures. The data is then numerically deconvolved to separate the spatial information from the spectroscopic information so that images can be reconstructed for each wavelength. The speaker then showed a video of the mapping strategy, keeping the telescope on the sunrise-sunset line, pointed 90 degrees away from the sun. The telescope images a small square region of the sky, rotates through a very small angle, and images the next overlapping square region. After several small movements, the spacecraft must slew through a much larger angle in the opposite direction to prevent the Earth's infrared emission from entering the telescope. As the spacecraft orbits the Earth, it traverses a great circle, imaging a complete ring of sky. As the Earth orbits the Sun, the great circle precesses, thereby mapping the entire sky. Bach said that it would take 6 months of continuous observation to achieve full sky coverage. Bach discussed the ways SphereX may help us answer scientific questions, including the search for water by absorption spectroscopy, the formation and evolution of galaxies by measuring extragalactic background light, and the nature of inflation in the early universe using 3-dimensional mapping of galaxies by galactic redshift. He said SphereX will provide a very rich all-sky spectral catalog with a complete near-infrared spectrum of every point in the sky, and therefore a large number of cosmic objects. These include galaxies, galaxy clusters, main sequence stars, brown dwarfs, quasars, asteroids, and comets. The speaker said that the data from SphereX would be processed and released to the public within 2 months of acquisition. Bach showed images of the assembly and transport of the SphereX spacecraft. He showed images of the SpaceX booster, the rocket fairing, and the payload bay of the Falcon 9 that was used to launch SphereX from Vandenberg Space Force Base in California. He showed a video of the launch, which took place in March of 2025. The speaker described the process by which the instrumentation was purged of water and cooled to the operating temperature. Bach showed the, quote, first light images obtained by SphereX on March 27th. The speaker ended his talk by saying, quote, "We have a happy spacecraft. The instrument is working well, and it is a very exciting time," end quote. The lecture was followed by a question and answer session. A member asked about galaxy formation. Does it appear that galaxies formed around pre-existing black holes, or did the black holes form inside the galaxies? And could SphereX provide information about the process? Bach replied that SphereX will give information about the ionization of matter during the period of galactic formation, but that unfortunately, SphereX will not be able to distinguish the source of the ionization. In other words, it cannot determine whether the ionization was caused by an accreting black hole or from the stars themselves. As a result, he said, you would need to investigate individual galaxies to get such information. A member asked whether SphereX could provide better estimates of the amount of space dust than previously measured, and whether such observations could affect the estimated quantity of dark matter in the universe. Bach replied that dark matter is presumed to be non-baryonic, not conventional matter, and that space dust was almost certainly baryonic. A guest on the live stream asked if SphereX could be used to measure the abundance of water in Kuiper belt objects, and if it could distinguish between amorphous and crystalline ice. Bach responded that the water absorption feature could be there, but that SphereX requires a light source to, quote, light up that feature. He said that this is extremely difficult to do with Kuiper belt objects and would be much easier for comets and asteroids. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the 2,514th meeting of the Society at 9:48 p.m. Eastern Time. Temperature in Washington, D.C., 21.7 degrees Celsius. Weather, mostly cloudy. Audience in the Powell Auditorium, 66. Viewers on the live stream, 38, for a total of 104 live viewers. Views of the video in the first 2 weeks, 370. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. We will entertain a motion to accept the minutes subject to that correction. A second. All members in favor? All members opposed? The minutes are accepted as read, subject to that one correction, and will be posted to the website in due course. And so we now turn to tonight's lecture by Carey Lisse. Carey is principal staff scientist in the Applied Physics Laboratory at Johns Hopkins University, which I believe prefers to be referred to as the Johns Hopkins University Applied Physics Laboratory. Prior to assuming his current role, he held a variety of posts at JHUAPL and at NASA. He began his career as an instrument scientist on the COBE project and then turned to planetary studies. Since then, he's focused his research on solar system fossils, like comets, particularly studying their X-ray emissions. He worked on deep impact from start to finish and observed dust excavated by the Deep Impact Impactor using the Spitzer Space Telescope. He also studied asteroids and X-ray emission from planets and searched for He also studied asteroids and X-ray emissions from planets and searched for the presence of asteroids and comets around other stars. Notably, in addition to Deep Impact, he has served as a member of the New Horizons and SpaceX science teams. SphereX science teams, not SpaceX science teams. I have Elon Musk on my mind. Among other honors, Carey received awards as part of the COBE team, the JPL Stardust Flight Team, the Epox 1 Flight Team, and the New Horizons Science Team. He is the recipient of a Space Telescope Science Institute Science Merit Award, a Space Foundation Space Achievement Award, a Johns Hopkins University Applied Physics Laboratory Special Achievement Award, and he was awarded the Isaac Newton Institute Visiting Fellowship at Cambridge University. He is a AAAS Fellow and the asteroid 122 626 Carey Lisse is named for Carey Lisse. He has appeared in many documentaries about planetary science and cosmology, and he previously spoke at PSW in 2016. He earned a BA in chemistry at Princeton, an MS in chemistry at UC Berkeley, and an MS and PhD in physics at the University of Maryland. All questions will be fielded after the lecture during the Q&A, as usual. And Carey, the stage is yours.
All right, thank you. And thank you for coming. Tonight's lecture is going to be on trying to understand what happened in the earliest epochs of our solar system. And hopefully, after I'm going to actually even show you some spectra, Larry said that was okay. And hopefully by the end of this evening, you will understand better about what our sun was in the year about 1 million years after it was just starting to turn on, just starting to glow and to shine. And let me ask, is the show and tell item, where is the iron meteorite? Can you start sending it around, please? Just hand it to folks. There's show and tell tonight. Reason to show up actually in person. Okay, so believe it or not, by the end of the night, I believe you will understand this picture here. And to give you an idea, this is what our sun looked like schematically at about 1 million years age. This is a protostar that is not shining by nuclear fusion. Instead, is shining by the accretion energy, but it's still growing and material is still glomming onto it. I want to thank my cast of colleagues, including Mike Sitka, who did a lot of the observations with me at the university on the Mauna Kea on Hawaii. Scott Woke, who spoke here, I think, 2 months ago, who is originally the reason why he and his colleague, Hans Moritz Gunther, are the reason why I started looking at RW Auriga. And my other colleagues, many of which are up at Space Telescope. Go next slide, please. Okay, 2 weeks ago, you heard Professor Jamie Bach talk about spherics and how spherics was going to look from the origin of our universe in a big bang that we think happened when the universe was smaller than a proton, and within a ridiculously short amount of time, expanded hugely at great temperatures and energies into a soup of subatomic particles, which had lots and lots of structure imprinted on it due to the fact that there were quantum fluctuations. I'm just going to show this. I'm actually got a lot of words on the next slide, so I'll just walk through this really quickly. Within a few 100,000 years, you get the surface of last scattering. This is what the CMBR, the cosmic microwave background radiation surveys have been looking at on the all sky. Then for about a few 100 million years, not much happens until the very first galaxies and stars start showing up. And we're walking along. We live over here in the present day. The important thing I'm trying to show in this is that from this huge explosion where everything was just a giant fog, hot fog, and a very quick expansion of our universe, there has been a process of over and over again of accretion and aggregation of bodies, be it clusters of galaxies to individual galaxies, to the stars inside the galaxies, and to the planets that are around the stars. So, I just said that in words. Quickly in words, I'll say it here is in a slide. We know the universe began in a fiery explosion 13.8 billion years ago. We know this explosion was highly uniform. It only was not uniform to maybe a few parts per million. Pretty small. In other words, pretty darn smooth. But that few parts per million over the size of the universe is enough to make all the galaxy structure and all the stars in the galaxies and all the planets around the stars that we see. And as I mentioned already, you see aggregation into giant galactic clusters, into the spinning galaxies, into the first stars. And remember that diagram I just showed you, which we're going to see a lot more? You're going to see stars are forming with accretion disks. And of those disks, there's clumping going on, which is where you get asteroids and comets and planets. And eventually those stars get hot enough in their center and they turn on and they start burning hydrogen and helium, but not yet, not in the 1 million years that we're going to be talking about. Why do you care, you, the customer? You and I are the products of this current of all this aggregation. All this stuff had to happen before we got here. And we're living around a about middle-aged star. The sun's 4.5 billion years old. It's got another 5 billion years or so to go. And the sun shines and all the energy we see, the food that we grow, the oil that we put in our cars, all the weather, the wind that we can harvest with giant windmills. These are all driven by solar energy. Probably the only thing that we use that isn't solar energy would be some geothermal energy coming from radioactives coming from the center of the core of our planet. So we need that sun. And we are also a product of that sun's formation. We're a leftover. Sorry, but it's kind of true. And I'll explain. So my job today is to explain to you about how this happened in the earliest times and how planets like ours formed. Okay, so let me set, this is a slide. I'm very proud of one slide from my 2016 talk. We live in a Milky Way galaxy that is a giant spiral pinwheel. This is it when we're looking down on it. It's a barred pinwheel. There's a bar at the center. And we are about 2/3 of the way out. If you want to see it on the side, here we are. It's about 28,000 light years to the center. We live, as I said in 2016 when I was talking about the prospects for life around nearby stars, we live in the burbs. We're way far out from the center, which can be one of the reasons why we haven't discovered anybody else yet, but that's another talk. Okay, but the point is that RW Auriga, which I'm going to talk about, well, I'm going to tell you it's 165 parsecs away, which is it's 470 light years. That's nothing in terms of distance compared to our distance to the center of the galaxy. This RW Auriga system is almost right on top of us. Okay? So here is a diagram showing you how we believe and how we understand solar systems form. What I'm going to talk about and show you is I'm going to walk you through these cartoons. What's really cool is that when I show you each one of these steps, I'm actually going to illustrate it with real data. So about 4.5 billion years ago, and point over here to get over there, about 5 solar masses, because this is a wasteful process, only one is going to wind up in our system, in a giant molecular cloud. And so part of that pinwheel, if you will, a clump forms in this pinwheel, most likely due to intersecting supernova explosions. When a supernova explodes, and they do that a few times a century, they put out more power than the rest of the galaxy combined. They're just huge explosion. And in your mind's eye, I want you to have that beautiful Star Wars kind of special effect. There's a giant spherical explosion that just goes out in all directions. And it's going to plow stuff in front of it. And if it runs into another explosion, or if it runs into one of these spiral arms, which is a density enhancement, it can cause collapse. And the collapse is a runaway process. Once a piece of matter hits another piece of matter and sticks together, it has more gravity. Then it's even better at collecting more material, and so on and so on. And what you get is a positive feedback and a runaway. You get collapse. This collapse occurs, and here's actually, if you were to go and look at Orion this winter, and you look in the Orion sword, if you know where that is, this is a picture in the Orion's nebula. So here's his belt, the 3 stars. There's a sword sticking down, and that's where you, with a telescope, could actually very easily see. These are little baby stars just forming now in Orion's sword region. Now, this all happens, this collapse, really quickly in terms of astronomical time, 10,000 years or so. Then, for the next about 1 million years, this collapse happens, but because the cloud had a net spin, there was some motion. It wasn't just a static cloud, just all forming onto a point. That would be highly unlikely. Possible, but unlikely. Is that you have to get rid of that angular momentum when you're trying to collapse into a point. And so what happens is your spherical cloud, or your roughly spherical cloud, is going to collapse into a point source and a spinning disk, which has the net angular momentum of that whole cloud. And as it gets smaller and smaller, just like when a skater pulls their arms in, they're going to spin faster and faster, and it's got to dump that angular momentum if the material wants to collapse and become part of the protostar. So what you get is this beautiful disk, and you'll get a bipolar outflow. You get jets. This happens for about 1 million years, and here's a beautiful example. This is a Herbig-Haro object, which has the disk you can see here and here. The protostar is sitting right in the center, and here's a red and a blue jet coming out of it. This is a very normal case and behavior, but it's important to point out this only happens for about 1 million years. Then, after 1 or 2 million years, the protostars are around. Then the jets turn off. You start forming planets. And the first planets, the giant planets. You still got a lot of gas around. You form comets and asteroids. And so that's our first comets date from these 2, 3, 4, 5 million years after the beginning of a solar system, including ours. And then by about 10 million years, the disk disappears. Then you get into the terrestrial planet forming times, and from 10 to 100 million years. And we're very especially interested in, because that's where our Earth and our Moon come in. Then after the terrestrial planets, rocky planets form, and they form slower because there's less material, but they don't have these giant envelopes that would choke us all. Then you get to the mature system, like we live in today. This is where you are, where you've cleaned out, there's no more disk, there's very few asteroid and comets, most everything is turned into planets or gotten thrown out of the system, and lo and behold, you live where we live. Okay, that was an astrophysical discussion. That's what people who look at stars and look at big globs of stuff and think about the galaxy and the pinwheel and all that. That's what they live in. This is what a planetary astronomer, and one of the things you'll hopefully, from the nice introduction I got, and from this talk, is I like to work across disciplines. And that's not just because it's a proclivity, it's more like there's no reason why one person's observations in, let's say, one field, astrophysics, shouldn't overlap and make sense in another person's field, planetary astronomy. So what does that mean in practice? Planetary astronomers look at the solar system today, our solar system. They don't tend to actually look outside of it. They don't worry about other stars. But they look at Mercury and Venus and the Earth and Mars. They look at the asteroid belt. They look at Jupiter and Saturn. They look at the Trojans that are moving around with Jupiter. Uranus and Neptune. They look at the Kuiper belt. And from the materials we can bring back, from the dynamical structure, how these orbits are established and how they look, where the bodies are and aren't, they try to work backwards to the time where the sun was just a baby protostar with a disk. They also use one other thing. Who's got the meteorite? If you could hold it up, please. They use what's in meteorites, what's in the solids that we have collected that are ancient. So I'm about to go talk this. This is the show and tell, so I'll skip to the second. What you are holding is, if you can hold it up, is a 4.5 billion year old piece of material. I hope you've all held it. I find it humbling and awe-inspiring. That is ancient. It has changed almost not at all since it's first formed. The only thing that's happened to it, it burnt a little on the top. What Lloyd is holding in his hand is actually a cut through it, so you can see a section. And that's a piece of a planetary core. You might have noticed that it's very dense. That's because it came from what's called a differentiated body, if you see here in the lower right. A body like our Earth was big enough that when it accreted, it was very hot. Everybody's idea that the Earth was a glowing hot ball of rock and it was melted through and through is correct. And eventually, the iron in it melts so much, and it's the densest stuff, it falls to the center. And so what you were holding there is actually very much like what material in our core is. That was from a failed planetesimal, something that got broken up, and we'll talk about that a lot at length. But this is a process called planetary differentiation. It happens due both to the energy of just accretion, of putting the body together, just the same way that I told you that a protostar like a T-Tauri star shines simply just by the energy of putting it together, and also from their radioactives. There's uranium and there's thorium and potassium that are putting out heat, radioactive heat. And the center of our Earth is glowing hot today, as you know when you look at a volcano. That heat is still coming in out from the center of the Earth. So I am not going to read you this Wikipedia page, but the reason it is here is because you are holding or held a piece of Campo de Cielo. It is an iron meteorite that's roughly 10 million years younger than the sun, but only that. It is 4.5 billion years old. It is extraterrestrial, so you held something not of this Earth. Aliens were not involved. It's a natural piece of material. It is very dense, as you noticed, and because it was dense, it wound up being in the center of a body. And the body has to be large enough to force it to the center, melt it, and turn and alter it. In order to do that, we think that body that it came from had to be at least a few hundred kilometers across. So think a few hundred miles. So something probably as big as the state of Texas or larger. I am not going to read any of this Wikipedia page. I am going to point out that you can learn, and hopefully this is one of the things you take away from tonight, and you can go and look up this page, and you can learn much more than I just told you about Campo. So let me go back just for a second. So now you've learned a little bit about meteorites, and this is a lot of the evidence besides the dynamical and the structure and our understanding of the current bodies that people can use to work their way back. And they can work back about, back to about 1 or 2 million years before the beginning of the solar system. But then, because literally the evidence has been baked, boiled, and altered, we can't do much more. Oops, wrong way. So things break down. I've literally just told you a little bit about, I've written through this slide, the objects we think that make the current asteroids. I should point out, this is this is a diagram from a recent asteroidal paper. The current asteroids, it's not as simple as stuff just got together, differentiated, and sat there. That would be much too easy for my colleagues, and that would follow Occam's razor. We think that almost all the asteroids we see today actually were born really big. Many of them differentiated and made a core, like the material you're holding, made igneous mantle, rocky mantle, and then made maybe an organic water-rich surface. And then lots of collisions happened, lots. And most of them got broken up, and then they reaccreted in the asteroids we see today. Like I said, it's more complicated. Impacts, do they happen? This is a picture of the south pole of the moon. There's impacts over impacts over impacts. The next time you look at the moon, I want you to look at it and think of it as a beautiful piece of archaeoastronomy. The moon has been just pummeled over the course of 4.5 billion years, especially we think in something called the late heavy bombardment 3.8 billion years ago. The important thing to think about is the Earth has just as much gravity as well. Earth has more gravity, 16 times bigger. We should have been just as pummeled as this. You need to think of the Earth as looking like this. However, we have weather, we have an atmosphere, we have water. Almost all those craters are gone. What the moon is a beautiful piece of archaeoastronomy showing you what happened to our planet. And we can work back 3.6, 3.8 billion years ago. We can't work back to 4.55 billion years ago. And I already mentioned what we do with meteorites. So I've just given you an instance, for example. This is one of the reasons to go to the moon again and understand. And we didn't know about the age of the moon rocks until the Apollo astronauts went there and brought them back. And we understood suddenly that what was going on. The moon is covered with these craters, and the craters all date to this 3.6 to 3.8 billion years ago. So what you're seeing is the evidence. If you look at the moon, if you take some binocs or just a minor telescope, you're seeing evidence for the late heavy bombardment. It's a frozen fossil time, just like the iron meteorite I was passing around. Okay, so what I'm not going to pass around, because it's much too fragile, is a piece of Murchison, which is another meteorite, which, unlike the metal meteorite I just showed you, which is not very common fall, but it is extraordinary, this is an ordinary chondrite, and in it, it has, maybe you can see it, little white blems and little tiny glassy spherules. If you look up on the picture there, this is a different picture of a similar, of a similar meteorite. But what you're seeing are CAIs, which is a fancy term for calcium aluminum inclusions. Translation, calcium aluminum oxides. Translation, ceramics, brick. Think of that stuff. Really high, hard to hurt, temperature and robust material. The first stuff that can actually precipitate out if the entire solar system has been boiled and baked, as I'll show you in the next slide. And with them also are these glassy chondrules, these little blems here. And this one, Allende, is just full of these. And these are the first solids ever made in the solar system. We can tell that when we look at the isotopic dating. We can look at the uranium and the thorium, the tungsten, the hafnium, and we can figure out how many atoms have decayed and how many haven't. These radioactives have billion-year lifetime, half-lives. So we can actually get good times and ages for these CAIs and these chondrules. And we're going to talk about these a lot. The important thing is that the CAIs look like the oldest things. And if you're a meteoriticist working in the solar system, you date everything from the CAIs. We don't know exactly what the sun was doing, but we know we have these solids. We can date them. And the chondrules come just a little bit after, within a few million years of the CAIs. So I want you to think, when you think them, as mentioned, refractory inclusion CAIs, think ceramics. When you think of the chondrules, think melted rock. Okay, everybody agrees in the meteoritics and the planetary astronomy community that these materials were made, somehow there was a high temperature spike, and then for the CAIs, they actually were cooled off really fast, and it was a huge temperature, about a factor of 10, maybe more than what made the chondrules. These guys also had a temperature spike, but cooled down slower. The problem is that people fight hugely over exactly what was the mechanism. Was it impacts? Was it shocks? Was it lightning in this disk I'm going to talk about? There are annual fights at the Lunar and Planetary Science Conference, which are very vociferous. And they haven't come to a conclusion in decades. I'm an observational astronomer. Models are nice, but I like reality. I like actually things I can reach out and look and see. I went to this meeting this year, and I was brave enough to give the talk I'm about to give to you. And I said, I think there's a system that looks like it's actually making these guys. I'm not going to tell you how it's made it. I'm just going to tell you there's lots and lots of data here. And if you want to spin your models, or you want to argue that it's your hypothesis works and this one doesn't, you've got to match what we're seeing here. So I'm coming along and saying, I think we actually have an observable test case that's going to help you understand the earliest solids in the solar system. This is just a plot. We call it equilibrium condensation. I apologize to the audience. Thought experiment: if you take everything in the solar system, unfortunately including the audience, and you evaporate it, and then you slowly cool it down, this is what would come out first. And the first is, these are the CAIs. That's that ceramics I was talking about. And then what comes out are olivine. And I think I have that. And that's going to get passed around too. Yep. So we're going to talk lots about olivine. This is the most common material in the early solar system. It makes up our mantle. If you would like to pass it around. For the ladies in the audience who like their gemstones, this is also known as peridot. It's magnesium-rich olivine silicate, if you like. Forsterite is the geological term for it. And we see this in primitive systems. It's extremely common. And it comes out next. And then and pyroxine's next, and then some metal, the iron nickel meteorite I was just showing you. And then a long way down, things like metal sulfides, and then organics and water. So again, the first things, it's not surprising that you're seeing ceramics and you're seeing chondrules, which are made of olivine, are the first solids in the solar system. Okay, this is a great story. I hopefully have spun it. You've understand it. You can go to the Smithsonian now and understand better. We've learned a lot, we planetary astronomers. So why do you need to involve the stellar astronomers in the study of the early solar system materials? As I mentioned, there are limits to what meteoritical studies can tell us, as the evidence has literally, for example, in the case of that iron meteorite, been baked, boiled, blasted, melted, differentiated, and in many cases, even submerged in water for millions of years. So the evidence gets kind of murky if you try to go back to within 1 million or 2 million years of t = 0. So another question, with 100 billion stars in our galaxy, that big pinwheel I was showing you, how come it took this long to go find an example like I'm about to talk about? And the short answer is that at 1 million years, if you look at your baby protostars, are surrounded by huge amounts of gas and dust. They haven't actually turned on enough and gotten hot enough that they blast away the giant cloud that they're formed from. They're usually embedded in, like these are. This is pictures of the Eagle Nebula taken from Hubble. And you can't see into the baby protostar's environment. So, oh well, that sounds kind of frustrating. We know they're there. We have a rough idea what they're doing, but we can't really understand them in detail. So, along comes RW Auriga. As I mentioned before, it's pretty close. And here's more audience homework. I'm not going to read the Wikipedia page, but it has it. Please go there after you hear this talk if you liked it. At plus 30 declination, it is directly overhead in December. Can everybody in the audience find Orion's belt, I hope? And if people know where the Pleiades is, this star is between Orion's belt and the Pleiades. It's in Taurus. That's the V. So you can see this very easily. This is also December is the prime time when we look at it from Hawaii. It's a member of the giant young Taurus Aurigae star-forming complex. As I'm about to tell you, it's a binary with 2 stars that are about 3 million age. The stars are both roughly about 1 solar mass, which means they're going to behave like the sun. Okay, this is what they look like. And I'm very proud to say the upper left, while it looks kind of like a blob, is actually 2 blobs. And this is data that I took and published in 2022 from Mauna Kea, Hawaii. Better resolution, this is these 2 stars right next to each other seen in the X-ray. And even better with the ALMA, the radio array, the Atacama Desert radio array, is here is A. This has much better resolution than the other 2 images. Here is B. And here is a giant bathtub ring. B orbits A every 2,300 years or so. And last time it passed by A, we think, was about 400 years ago. Those numbers are going to be very important. Okay, so what do these T-Tauri stars look like? I told you I'd come back to this diagram and hopefully it won't scare you too much. Protostars here, it has these little things that look like wires or hair. Those are actually magnetic field lines that go from the protostar surface to the inner disk accretion wall, the inner wall of the accretion disk. And I'll explain what this is all about in a second. And then there's this big accretion disk that goes from 0.05 AU, so just a few times the stellar radius, all the way out to the edge of the Kuiper belt. One of the reasons this disk is important is that if our sun went through this very same phase, the edge of this accretion disk is going to be where the future Kuiper belt's going to be. It's the edge of stuff, where there's still enough stuff to make snowballs in this case, make things the size of the moon or smaller. Inside this disk is a huge amount of material. This disk weighs about 1/10 of a solar mass. So that's a few hundred times the mass of our planets. There is plenty of stuff. This is where the planets are going to form. This is where asteroids and comets are going to form. And it's also extremely cold here because it's what we call optically thick. The light from the star can only get to about maybe in here. Everything else here is sitting very, very cold, like the cold of the outer space. So even ices like nitrogen and carbon monoxide and methane can condense here, the stuff that we see in comets, and only stable way far away from our current sun. So there's a lot of things going on in here, the very beginnings of the solar system. The surface of this star is glowing about 4,000 to 5,000 Kelvin. That's a little surprising. As I told you before, and I'm going to show you again in the next slide, the star is not shining by hydrogen fusion. It hasn't gotten there yet. What it's shining by is material coming from the inner disk wall, following magnetic field lines and dumping onto the star at certain latitudes, which again I'll show you in a diagram or two. And all that energy is getting dumped in a small region of this protostar, enough so you get X-rays, the local places where it's getting dumped. And it is shining within about half to 2/3 of the luminosity you see from our sun. This protostar is actually very, very highly energetic, and it's all coming just from the self-ascending, just the energy of stuff dumping onto it. So there's a lot of dynamics going on. A lot of things are getting mixed around and moved around here. Okay, why is this important? Trust me, if you hang on for one more second or two more slides, I'll explain why this is important. So this is what's called the Hertzsprung-Russell diagram for stars. This is called the main sequence, where I'm following up here. This means that if you're burning hydrogen to helium like in a normal star, that if we know your mass, we know your temperature, and we know your luminosity. So when you look in the night sky, if you see a blue-white star, we know that it has to be a lot heavier, a lot more massive than the sun. The sun lives here at 1 solar mass. Blue-white stars are up over here. We also know how long you're going to live. It's actually very predictive. What you normally don't hear, and the faintest red stars, little red dwarfs, which live forever, live down here, and they're like 1/10 of a solar mass. What we don't usually talk about is how stars first collect their mass and their protostars, and then they eventually wind up being on the main sequence. It's called a Hayashi track. This is where the luminosity is just decreasing as the star is getting smaller and smaller. It's collapsing, it's absorbing mass, but it's not changing in color. It's just pretty much going straight down. And we know that these are 3 million-year-old stars, so this is where A is going to wind up over here, and B is going to wind up over here once it starts burning hydrogen and helium. Stellar destiny, if you will. So we know what these guys are doing. We know that currently they're redder than they will be once they're normal, average, everyday stars. But we know that there's an awful lot of energy is coming just from dynamical motion and aggregation and accretion onto the protostar. Okay, when we look at A and B up close, we see something very interesting. Pardon me. B is doing what every self-respecting T-Tauri star of 3 million years old is doing. It's got maybe a protostar at the center, but that's not where the brightness is coming from. It's coming from a beautiful ring where a planet's forming. That's what it should be doing. And this is looking into the details of that Alm image I showed you before. And B is over here. A is over here about 230 AU away. So it's about 5 times the distance from us to Pluto. Well, no, excuse me, about 8 times the distance from us to Pluto. So these guys are next door, but not too close together. And A looks nothing like this. There is no planet forming. A looks like a very primitive system. It's just got a central condensation, and it's got what we call a power law disk. There is no structure here. There is no planets forming. A looks much more like what a 1 million-year-old system looks like, not a 3 million-year-old system. This emphasizes that if you take an ALMA survey of the T-Tauri stars in Taurus Auriga, you'll notice that the vast majority of these systems have nice planetary rings. They're doing what you're supposed to do, what we think planet systems do this time. On the other hand, A looks very primitive. So does another system called DG Tau, which we're starting to get very interested. So we notice that A seems unusual. A is unusual for another reason. Remember those bipolar jets I talked about very early in the history of one of these systems? A has got a beautiful set of them. B has no such thing. And these jets we're going to talk about those a lot, but A is throwing stuff out in a bipolar jet, and the jets are seen very much in iron and sulfur, which is going to be part of our tail in a little bit. And you might notice that there's knots, there's clumps here, and the clumps have been seen to move over time, and folks can actually work out what is the velocity of the material in a jet, and it's fast. It's somewhere between 100 and 200 kilometers per second. Okay, that's rather fast, and it's going to be very useful for us because I use a spectrometer in Hawaii that actually can detect the 100 to 200 kilometers per second differences. Okay, hopefully I talked a little bit about and explained to you and excited you a little bit about what RW Auriga can do. Here's where it starts getting really interesting. This is the light curve for RW Auriga over the last 20 years. You might notice it has a bit of a variation normally, just kind of this, and then wham, in 2014 it had this huge drop. And that drop didn't come back up to normal for another 6 years. And then it goes back to roughly its normal behavior, and I will take away my own thunder. We're starting at wham again. And we'll come back to that. And you might notice that there's also this notice here that Chandra observations. That's because my colleagues Woke and Gunther are the folks who first pointed me to RW Auriga, because they were watching this system and they saw the normal X-rays. Remember I told you how stuff dumps onto the protostar and latitudinal bands follows these magnetic fields, and there's a huge amount of energy dumped right here and right here, southern and northern latitudes. And these are X-ray emission regions from the protostar. So you can study these T-Tauri stars in X-rays. And this is the first spectrum. I will, hopefully people understand spectra, but I will explain a little bit more. This is the normal X-ray emission coming from the surface of a protostar, from RW Auriga A. And what you're seeing on the horizontal axis is the energy of the photon that we're measuring. On the vertical axis is basically the number of photons we see at different energies. And the characteristic peaks tell us these are due to certain atoms. One here, this is due to, I believe this is silicon and this is aluminum. And so we normally see some silicon and aluminum that are being dumped onto the star and heated to very high temperatures and emitting X-rays. Well, in 2015, Chandra went back and the normal red spectrum was totally gone. In fact, there was almost no X-rays. What that tells you is that a huge amount of material got between us, Chandra, if you will, and the surface of this protostar. By the time 2017 rolls around, some of this stuff is dissipated, this absorbing stuff. And then there's this huge characteristic 6.2 keV line, which is very well known in the X-ray community. This is iron. So it is thought that a huge amount of iron, roughly about 10 to the 19 kilograms of iron, has shown up in this region around the protostar. This number, I will translate it, I'm going to say it again later, is about the mass of the core of the asteroid Vesta. This is not a trivial. Vesta is one of the 4 biggest asteroids that we have. And it's known to be very primitive and very igneous. So this is important. We're seeing what looked to be like an asteroid got broken up and destroyed. And that's what the X-ray folks published in 2018. And because I was working with them and because I've been doing a lot of stellar astronomy, I thought that maybe I might go look at it with the near infrared. One last thing I'll say before I go. If you remember that I was showing you the T-Tauri star before and I was showing you kind of the disk from kind of an oblique angle, this is if you look at it from the side. Here's your protostar. Here's those magnetic field lines. Here's the inner edge of the accretion disk. These temperatures here are something around 1300, 1400 Kelvin, very hot. That's hot enough to blast rock, by the way, very important number. And here's the rest of the accretion disk. So what the X-ray guys thought was basically this system may have gotten a very strong case of indigestion. There's a normal amount of accretion that happens from the disk and slowly dumps onto the protostar. It's something like 10 to the minus 8 to 10 to the minus 7 solar masses a year. What that works out translation, this system is 3 million years old. In 3 million years, it has accreted roughly somewhere between 0.03 to 0.05 solar masses, which is a lot of material. And normally that just happens with little pieces of dust and gas. But every now and then, a big, if you will, boulder comes through. A big asteroid, and gives the system an indigestion. It overloads the accretion mechanism. And suddenly, somehow, it breaks up and gets destroyed, creates a huge amount of material in the inner region, which obscures the baby protostar, and creates a violent event. And we're going to talk, hopefully, I'll promulgate the idea that that violent event is what makes your chondrules and your CIs. Remember, they're high-temperature alteration products of normal rock, of wherever the olivine is. Okay, so I came along because these are X-ray folks are my friends, and I've been working with them looking at X-rays from comets and other things. And I said, hey, we know how to do stellar spectroscopy. I've been looking for the abundances of stars that host planets and trying to compare their abundances to our stars' abundances and see whether there was something unique or different, blah, blah, blah. The important point is I knew that there were lots and lots of good iron lines in the near infrared, which I could go and then test the X-ray folks' idea that they just saw a lot of new iron gas. And the short answer is that I went out and we got this beautiful spectrum you see in the black. And this is spectrum of RW Auriga A. Remember, this is the one that's acting out, that's acting very youthful, has jets, no structure to it. And here's B, which looks just like a normal 3 million year old star making planets. It's doing what it's supposed to do. And you'll notice there's a huge difference. The accretion disk of A is much, much hotter and brighter than that of B. You'll notice, see all these little spikes? These are not noise. These are huge atomic emission lines. There's lots and lots and lots of hot gas in A. all those emission lines in A, they're all an absorption in B. They're all cold gas, just absorbing light from that star. And here's an example of a beautiful iron 2 emission line. We saw lots and lots of iron lines. And this is what it normally looks like before there was any upset. You'll notice that it had this huge spike, and it has structure, and eventually went down and dissipated and went back in 2020 to that behavior. I made some noise before about jets and how fast they're moving. What you're seeing here are red and blue shifted jet line emission. That 100 and 200 kilometers per second is so fast that even with SPECS, which is for the experts, RW 2000, it's a moderate resolution spectrograph, was able to see the jet emission and what we call the bifurcated lines. So I'm able to separate what's getting thrown into the jets from what's dumping onto the star. Just mentioned that before. Here's our 100 to 200 kilometers per second. I should say that independently of that number, I actually just dug that paper up recently, I can simply just see what is the Doppler shift, what is the difference between the line center here and this peak, and I worked out about 120 kilometers per second. So independently, we came up with what we thought were the jet velocities, and then lo and behold, these folks were looking at the clots moving, come up with numbers like this. So very consistent. Now, you don't have to believe me that I know what I'm doing with bifurcated lines. Takami et al. In 2020 published a paper saying, whoops, hey, guess what? We've been watching RW Auriga A and iron 2 at one different wavelength, but I'm looking at the same kind of species. And lo and behold, here's 2014. Now, then suddenly 2017 got a lot brighter, and even a blob started coming out on one of those clumps. So the jet was active. So we were measuring spectroscopically what we were seeing and inferring, they were seeing in imaging. And they came out with a velocity very similar to ours. Okay, so these are pretty pictures I found from the web. I just want to, hopefully you'll have these in your mind. New talk slide, trying to see if this works. They're showing the same thing in different ways. Baby protostar, here's your accretion disk. Stuff is getting moving down into the center. Some of it gets accreted. There's bipolar outflow in the jets. And we think that CIS and chondrules are happening in the really hot places right in here, right next to the protostar. Okay. Slight change. I do lots of different kinds of analyses, and one of the things I do is called astromineralogy, and this is where the olivine story is going to come in. So not only do we do atomic line emission spectroscopy, like I just showed you, and prove that there's iron 2, not only in X-rays, but we see it in the near infrared, and we see it getting blown out of the jets, but we can actually just look at the dust that's in the accretion disk. And I got into this game because I was part of the Deep Impact project, as Larry very nicely mentioned. And my job on Deep Impact was to take the Spitzer Space Telescope and watch the impact happen and see what got blown out of a comet, which was material made in the beginning of the solar system. Very much like that iron meteorite, but a material that had never been heat treated, that was just stuck into a very cold snowball and left out to freeze. And the short answer is we got this beautiful spectrum you're seeing here. And there were 16 different unique features. I'm going to show that in the next slide. We got this beautiful spectrum. This is what Deep Impact, what Tempel 1, the comet, looked like before we hit it. This is what it looked like after we hit it. And we got this beautiful spectrum, which I could tease out all kinds of different materials. And then we could compare those materials to what Stardust collected and brought back from a comet, and we got very good agreement. So what I'm trying to say is I'm pretty good at figuring out from a mid-infrared spectrum of dust, and this goes from 5 to 35 microns, not the 1 to 5 I was showing you before, we can actually figure out how much olivine and how much pyroxene and how much organics is in it. And every now and then, we can also look at a system that doesn't have the normal olivine and pyroxene, the normal rock you're seeing. Very few, but finite number of systems we've seen have what's called silica, stuff that's in your window glass, stuff that's your beach sand, stuff that is not normal, that is not that olivine. It is blasted and altered material. And so we're pretty good at figuring out how to find that. Okay, that all being said, and we don't see, by the way, so this is the, if you want hands-on, this is the list, a visual list of the materials we found in Comet Tempel 1. Water ice and olivines and pyroxenes, clays and carbonates, metal sulfides. You do not notice silica here. There's no window glass. There's no altered obsidian volcanic glass or tektites. And this is what Stardust saw. So What do we see when we go and we look at RW Auriga with the mid-infrared? What we see is this busy spectrum, and don't worry, I'll walk you through it. And I know it's got a bunch of wiggles, but let me tell you that the first wiggle we look at is this. This is the protostar surface, and it's what we call a 4,000 degree Kelvin black body. If I look at these lamps overhead and I were to shine my spectrometer at them, I could actually tell you what the temperature of the light, and I would see a certain spectrum, and it would peak in the visible. These guys are probably, I had to guess, orange, white, probably about 4,000. They're about the same temperature as our protostars. If you want to think of it differently, everybody's worked with an iron in a fire, and you've seen different colors in that iron, right? You know how it can be cherry red and start heating it up, it gets to a kind of an orange red, and then a yellow red, then a white red, then a kind of glaring white. Those are what we call color temperatures, and all you're seeing is black body radiation, which is shifting its peak because it's getting hotter and hotter and hotter. It's the same reason when you look at stars in the sky, the red stars you can see, there's a few of them, they're the coolest ones. The yellow-red ones are a bit hotter. And then our sun is yellowish-whitish. And then if you can see the blue-white ones, they're the ones that dominate the night sky. They're really hot. That's just black body temperature. We call it color temperature. So the short answer is we have the surface of the protostar. We can also see that there's a diagnostic. There's about 190 Kelvin dust in the accretion disk, the average temperature of the dust in the accretion disk. But what's important when I remove all those black bodies and all this stuff, the basic stuff, is this red spectrum, which has very interesting structure to it. And it has emissions due to things like olivines and pyroxenes, but it also has lots of silica and lots of alumina. Silica is in chondrules, and the alumina is in the CAIs. We see evidence already. This was taken in 2007 with Spitzer for CAI and chondrule material in RW Auriga. Now, there's a problem with this in that this is a combined spectrum because Spitzer was only so good. You couldn't separate those two stars. JWST has come along, brand new, and actually separates A and B. So we have a spectrum of A now and a spectrum of B. And I'm going to go to that quickly. And I'll also point out really quickly, A's got a huge number of emission lines. Lots of these are water, like we were talking about tonight over dinner. You were talking about formation of water in early young systems. This guy's got lots of it. Also got a lot of CO2. So I have not yet modeled it because I haven't had the time, but I can tell you that this is where the nerd factor is going to come in. You show me a spectrum like this, I will sit down with it for hours. I will tell you immediately, oh, look, there's water. Oh, there's carbonates, like chalk. Oh, look over here, there's silica, and there's silica over there. And look, this is very broad, which means it's very amorphous, and there's lots of silica, which is not normal versus the silicates. And oh, this guy looks like just olivines and pyroxenes like it should be. This is B. This is the normal system, doing what it should be. It doesn't have much water in it, a little bit. And this is what you would normally see, kind of the silicates and mid-infrared spectrum of comets. This has got all kinds of stuff going on in it, like hot water, hot CO2, carbonates. As I said, lots of it looks like I have to find the alumina, but certainly has silica. This is highly altered and blasted rock. And this is what I'm going to be doing for the next year and a half with JWST. And this is very exciting. Okay, so hopefully I got you. That's really fun for me, maybe not as much fun for you, but that's the characteristic. If you want to think of it like CSI, if you give me a spectrum, some of the experts like me, we'll tell you within 5 minutes, we can tell you, what didn't take us very long to tell you what was the makeup of that dust. We need to do a lot more detailed modeling to make sure and look at the subtleties and check out the ratios of everything, but we know already that there's lots of chondrules and CEIs. What's going to be really interesting is, hopefully I'm putting it across, this is the system in 2007. This is the system in 2023. So we have two different measures of the dust. And remember, this is before that big upset. This is after that big upset. So we're going to be able to see if there was a change and if there was a new amount of chondrules and CA-like material has shown up. In this case, because Spitzer couldn't separate them, this is A and B. And I'm sorry if I confused you. I purposely, while JWST can actually do the two independent, this is A and this is B, I have purposely added them together to show you direct comparison. Because remember, Spitzer couldn't separate. So this is the combined spectrum from JWST. It's actually removing JWST's wonderful spatial resolution. But, well, I think we should take it at the end. But so the other thing I want to say real fast, time might be getting short, is that remember I told about all these atomic emission lines? There isn't just iron there. The X-ray guys could find iron, but we can find lots more. So if I zoom in on this spectrum and I show you the region right in here, about 1 micron, there are a whole bunch of sulfur lines in here. Okay, you got to trust me on this one. I had to look them up. There's lots and lots, and you'll notice they're bifurcated, just like they're in the jets. There's a lot of sulfur coming out in those jets along with the iron. And I'll cut to the chase and hopefully make it exciting for you. There's about 3% or so iron in our core. It's in there with the sulfur with the iron in the core. And I'm finding about 2% versus iron. So we're seeing what looks like a blasted and destroyed core of a planetesimal is getting thrown out. If you were to take that iron meteorite, and don't you dare, but if you were to evaporate it and throw out the jets of the system, this is what you would see. We were also seeing a lot of silicon. And silicon, turns out, there is supposed to be about 1% to 2% silicon in our core. So we think that we're measuring core material. So RW Auriga may not only show us how CIs and chondrules are made, but it may actually be able to allow us to destructively measure the composition of a planetesimal core. That's a unique thing. If you talk to people who study our own core, they'll tell you that it's about 10% too undense. They'll tell you it's almost all nickel iron, but they said that 10% of the material has to be less dense than iron. They can't tell. They argue about whether it's silicon or sulfur or carbon. They can't tell you exactly which species from the density measurements, and nobody's ever gotten a piece of our core directly. But indirect inferences like this may be very useful to them. Okay, here's where we get some surprises. There's 2 things. One is nitrogen at 1.04 microns, and nitrogen is an inert gas. We don't particularly expect it to be in the core. There is some recent work by a group that says that actually at high pressure, nitrogen actually it becomes a siderophile. It'll dissolve in iron. So maybe that's the reason. But I'm going to tell you an even stranger material, which is helium. We're seeing beautiful bifurcated signatures of helium now and during the previous upset. And we don't see them of hydrogen. This is a hydrogen line. It looks beautifully singly peaked. There's just to show you that we do measure singly peaked emission lines. So there's no hydrogen. And the thing is that if I were to take, here's the chemist in me coming out, if I take a core made of that material I was passing around, and it's hot, it's liquid possibly, I would expect the hydrogen to dissolve in it much better than the helium. Helium's unreactive. It doesn't care. It's not going to do anything. So it seems strange that there's a lot of helium. I then thought about what about if there's a lot of radioactives giving off alpha particles. Problem is that short-lived radioactives are almost all beta emitters. We don't know anything that puts out a lot of alpha particles, which are helium, in short periods of time. So this is a bit of a mystery, but we think we have an answer to this. I'll explain in a minute. Okay, so let's talk about the big picture, in case I haven't said it well. RW Auriga, what we're seeing here is consistent with the idea that asteroids are all formed big. You made a whole bunch of series in Vestas. You make them really fast because it's easy to agglomerate really big things. Remember that positive feedback? You're not going to make lots of little things. You're going to make bigger and bigger things as long as you got materials. Then what happens is that these guys come in and then they get lots and lots of collisions happen. They get broken up into pieces. Some of them reaggregate into things that we see today. Some of them stay as little tiny pieces. And so this is the current picture for, again, forming asteroids in our own asteroid belt. Well, we think we've got something that looks like it's about the mass of Vesta, because we saw the core, which is about 10% of this mass. We got that much iron. And we think that we just saw it getting destroyed. What's also interesting, I'm going to go through this quickly, is this process an important process? What we've just seen, and if you agree that we've made chondrules and CIs by whatever mechanism, is it an important mechanism? Because there's a lot of mass in this disk. The short answer is if I just do a back of the envelope calculation and I figure out, okay, every 6 years and got another few million years to run, 1 million years to run, how much material am I going to be able to transform over? And the short answer is about 10 to the 27 kilograms if this process happens. And remember, the jets had clumps in them. It looks like this has been happening again and again and again. So the short answer is that it looks like, roughly speaking, I can process about 50% if every 6 years I blow up another one of these asteroids. So remember, that's an upper limit. And we don't think that every 6 years this happens because there's stochastic events. So, but the important bottom line here is that this is possibly an important mechanism for transforming materials in very young accretion disks and making the chondrules and the CEIs, which are so prevalent when you look at very young solar system materials like this. Pristine. Okay, remember I showed you before I took away my own thunder? Well, here's that huge drop from 2014 to 2020. I didn't get on it with my colleague, didn't hear from my X-ray colleagues until here. What we think is happening, if you look here, is this same kind of huge drop, but now we're starting at the very beginning. So now we can actually see the whole process. And I was lucky enough to be working with my colleague Mike Sitko, my partner in crime at the IRTF facility out in Mauna Kea. And remember I showed you this spectrum we had? This is what we saw for RW Auriga during its relatively benign phase. Here's what we just got on March 17th, almost a month ago. And you'll notice that while this part over here is about the same level as here, this brightness, this flux over here is about 1/10 and a very different structure of what we had before. We're getting a huge amount of extinction. There's a lot of new material on top of that protostar obscuring it again. So this light curve drop makes sense, and we're seeing it spectrally, and we're seeing also, they're back, our bifurcated lines. The jets have just gotten pumped up again. So cool. I hope you all get the feeling that this is an interesting story, but it's also one that's very much in development. We're still learning about this, what's going on. We needed to see these again, and we do, but seeing them come back is telling us that this is a very important signature. And it is likely that what we're seeing are those clumps are actually destroyed planetesimals. And if I haven't said it very clearly, the astrophysics community has never actually looked at those jets. Oh, let me back up before I say that. And said, aha, why do we see the jets only in iron and sulfur? Or why are they episodic? They just describe them. You had to take somebody with planetary eyes as well to say, iron and sulfur, that's in planetary cores. And episodic destruction of asteroids is something that we think happens all the time in the early solar system. So these are, I'm connecting them. If you will, I'm conflating them. We still need to prove that this is the case, but we think we have a pretty good darn proof of it. One other thing I'll throw out here while we're talking about why this system is wonderful is there's a new class of objects that some people have reported. It's called jumbos, which stands for Jupiter mass binary objects. Folks have found what look to be free-floating planets that are binaries. These have been reported. It sounds kind of crazy. And they claim they found a few hundred of these. Okay, and they claim that they find them in interactions, or modelers claim, between two young stars with disks. If you look up here, so here's one star, here's another, it could be RW Auriga A and B, for example, and you blow up this region here, they can create two little planetary clots that condense. If you look at the numbers here for the times, you'll notice these are like thousands of years. Well, that's the orbital time period for our two guys. The separation here is a few hundred AU. That's the separation here. Okay, fine. So why is Casey going on about this? Well, if you look very carefully at this map, here's A and here's B. See that little clot down there? Or in the contour plot, see that? That's always bugged me. What if that's a jumbo? So I have talked to this group and said, what if this is a jumbo? Can you model it? And they'll get back to me. So again, this could be another laboratory for very young solar system formation processes. So I hope you understand why I'm excited about this. Here are my conclusions, which I will read through. So RW Auriga A, even though it's got a nominal 3 million year age, is very much acting like a rejuvenated 1 million year old T-Tauri star. Because it has that excited atomic emission lines, because it has jets, because it has an accretion disk, which looks like it is actively accreting. The advantage of this being, if you will, a 3 million year old is it's blown off its enveloping, obscuring gas and dust. We can see right down into the center. We can watch the processes that are happening. And so that's the advantage. It's acting like a very young system, and it can tell us. And yes, it's not exactly an analog for the solar system. It's a binary, and it's a little bit older in some ways. It's a little peculiar. That being said, this is the first time we've ever been able to see system-wide processes in something that's acting sort of like a million-year-old system. And hopefully from here, we can bootstrap and learn more. I mentioned there was a recent massive system-wide stochastic event lasted for about 6 years. I mentioned that from both the X-ray and from our near-infrared jet measurements, that about 10 to the 19 kilograms of iron and sulfur got blown out of those jets. I've mentioned that that's about the mass of Vesta, one of our largest asteroids, and that's very, very consistent with asteroids were formed big. I mentioned also there's mid-infrared spectral evidence for the presence of new chondrules and CAIs. So we're making the earliest solar system solids. Oh, if I haven't said it, that accretion disk, the abundance and what's in the accretion disk should just be like interstellar matter. Should be hydrogen and helium and and maybe atoms of silicon and iron, but nothing. There shouldn't be much solids in it. Everything in solids is actually getting created as it's coming into the protostar and getting processed. The measured conditions in the inner disk wall region are very consistent with models of chondrule and CI formation. It's hot enough down there to blast and alter rock, especially if you take a planetesimal and crash it into another one. So we are, if you will, if you want to ask me what I think is happening, but we need to hear from the modelers, I think that you took a Vesta-sized differentiated asteroid, you migrated it in from a few AU, and how you broke it up, I'm ecumenical, but maybe you hit another one, and two of them collided and broke each other up. That's what we wrote about in 22. However, given everything that we've been talking about, remember that helium and the nitrogen I mentioned, and was a little bit of a puzzle. So I think that what may be happening is you don't maybe have to break up your objects. It could be easier than that. At the LPSC this year, when I was talking, I also heard a really interesting talk about people modeling the asteroid 16 Psyche, which is the target of the Psyche mission. And the way to make Psyche is to actually have metal cores for very young planetesimals be liquid for a long time. And then I went, aha, RW Auriga is not that old. What if it's got a liquid core? That's a heck of a lot easier to break up and disperse and boil off into gas than a solid one is. So we are now, I'm actually looking for a better name for it, talking about the leaky punctured jelly donut model. So what if you have a rocky planetesimal, mostly rock on the surface, but it's got liquid jelly core, and all you have to do is punch through it. The core is at high pressure. It'll get sprayed out. And helium and nitrogen, which don't necessarily have to be in the core, they can just be inside the planetesimal, because remember, it's a mix of just ISM material and it's never had a chance to outgas. You simply have punctured this jelly donut, and the helium and the nitrogen spurts out too. So this is how hypotheses are built. I'm not saying that's necessarily the answer, but it's a hypothesis that fits the observable data, and I want people to poke at it and model it and think what can be. I tend to write observational papers. This, what you've heard, is going to be written up once we've worked at JWST. We're going to say, this is what we think we found. Now, you guys tell me what we think we found. And again, we should be very excited because this is another giant stochastic event is happening in this system, and we can learn even more. So one of the reasons I'm on the warpath, and I've been giving this talk over and over in the last month and a half, I want everybody to look at it with all their telescopes and all their observatories. And we should hopefully learn a lot more about how you make early solar system in the first million years or so. And I've also mentioned the jumbos, and that we've talked to the modelers, and we'll see what they have to say. Finally, thank you for your attention. You've been a great audience. I hope you like this talk. I hope you're a little more intrigued and not too scared by spectra and T-Tauri diagrams. And I would love to hear from you if you have any ideas about what you think is going on or like to learn more about this system. Thank you.
My goodness, and to think only a few decades ago we didn't know anything about any exoplanets anywhere. So we have time for some questions. Now, we'll start with the blue microphone.
Thanks for your talk. I'm Joe Foreman. I'm a life member. And I was reading recently that earthquake seismologists have postulated that the inside the liquid core of the Earth is a solid ball.
Yes.
I don't know if you've heard about this, but
Yes.
since solids can handle shear waves and liquids can only handle pressure waves, is this consistent with your observation, or what do you think about this?
I think it's, thank you for your question. It is entirely consistent. And originally we had thought that maybe our core was just solid. The Earth's core, if you look at the history and the models, did start out liquid. What happens is the proto-Earth assembles, it gets hot on the inside, and it gets hot enough eventually to melt the metal sulfides in it, and they actually percolate out. It's called iron rain. They actually percolate through the rock, and they're much denser, and eventually they collect into the center of the Earth. When they do that, they are not solid. So early on, the core of the Earth was liquid. Now, this is 4.5 billion years ago. The Earth has been the core has been crystallizing, and in fact, it's still crystallizing today. The liquid outer part of the core is thought to actually be slowly diminishing, and the energy of solidification is actually still helping to heat the rest of the core and the rest of the inner Earth. So that's actually very consistent. What you are suggesting, however, we have to be careful. If I'm talking about a Vesta-sized planetesimal, it's got much lower, the temperatures and the pressures are much lower than what is in the Earth. The bigger the body you are, the more radioactives, the higher the pressure. So they could follow a little bit different trajectories, if you will. But still, the very first part of core formation involves making liquid iron and liquid iron sulfides.
Red microphone.
Mike Aubrey, I'm a member. Could you explain the physical mechanism for creating the jets, the polar jets? I don't understand how they're produced.
Oh, you and most astronomers. Astrophysical jets are still a bit of a mystery. We know we see them. We're not making these up. We can see them in many, many systems. You see them, everything from black holes and accretion. We see them coming out of the AGNs and galaxies. We see them around T-Tauri stars that they're very young. We understand that they are extracting energy and angular momentum from the system. We don't understand the exact physics. It's very complicated. I can give you a hand-wavy argument, which is if I'm a protostar and here's a spinning disk and I'm trying to become part of the central star, I have to get rid of that angular momentum. And in order to do that, if I go in, I have to sacrifice that angular momentum has to come out somewhere else. And just the way that can happen if another piece of matter that I've just interacted with spins out and takes a lot energetically and takes away the energy and the angular momentum. If that makes some sense?
He nods his head no.
I can tell you that just the same way that people still argue about chondrule and CIs, the jet structure and formation is not very well understood. I will point out to you that I went over it a little bit quickly. The protostar is spinning with about in this case, 2.6 day period. So that's pretty fast. That's 10 times faster than the sun. So you've got an object that's about, well, in this case it's 1.2. This object's a little more massive than the sun now. It has got a lot of angular momentum. And it is spinning. Our sun, by the way, was also spinning with just a few day period when it was this age. It has slowed down over the giga years by throwing out mostly the solar wind. The solar wind carries a lot of angular momentum and energy with it. Very slowly, but it's done that over billions of years. So again, I may not be answering your question directly. We don't understand exactly how jets form. We do understand that they're there. You can imagine how when stuff starts falling down that it can actually start making a jet. But I don't think I can point you to some papers. But again, I don't understand the process myself. If I did, I would tell you.
So you can feel good.
Yes.
We have blue microphone, please.
Hi, my name is AJ Kotari. I'm a member. My question is about this. You hear that there are some elements which are primordial elements, like thorium-232, uranium-235, 238, etc. When are they formed in this thing? I mean, I don't see any. Obviously, there are heavier elements near the end of the periodic table.
Where do they come from, and how do we use them to date our meteorites, for example?
Yeah.
So you've probably heard the statement that we are all stardust. I went a little quickly, but the galaxy, so the Big Bang happens 13.8 billion years ago. Our galaxy is roughly 12 billion years ago. Our sun is only 4.5 billion years. So everything in this room, again, apologies to the audience, all our atoms have been through, if you will, the guts of other stars. They've all been, the heavy elements have all been created, not in the Big Bang, but actually by stellar nucleosynthesis, by the burning of hydrogen to helium, helium to carbon and nitrogen and oxygen.
Right.
And that's how you can get up to iron. But then you're asking for the really heavy elements,
Right.
mainly supernovae and in neutron star mergers, we think now. You going past iron takes energy, and it's very unlikely. And also because you're collecting, in case of uranium-238, you're collecting a huge number of protons and neutrons in one place, which is unlikely. But what you can do in a supernova, you can have a massive explosion that mainly just throws out a lot of hydrogen and helium and maybe burns stuff to iron, but a tiny fraction of a percent is going to get of those atoms are going to get inundated with a huge flux of neutrinos and neutrons and protons, and they'll actually do nucleosynthesis. It's called the rapid process. And so you can make radioactives in highly energetic events like neutron star mergers and supernova. And that stuff, the half-life for uranium-238 is about how to do this right.
14.7 billion.
It's long. So if you make it into supernova, you can simply, it will just float around in the interstellar medium until this cloud collapses. It comes with the cloud. And so you didn't make it in the protostar at all. It just gets involved. And then once it gets put into a solid phase, you can then figure out how many of those atoms have decayed and turned into thorium and radon and radium, et cetera, and go eventually to lead, or in the case of radioactive tungsten, into hafnium. And you can use these as clocks. That's how we can get the incredibly accurate times for our meteoritic materials. That's how I could tell you that that iron meteorite, wherever it is, again, I want it back, is only 10 million years younger than the sun. If you think about it, we're almost positive the sun is 4.56 billion years old, and I'm telling you that iron meteorite is 4.55. That's a pretty good accuracy for something that old. Hopefully I answered your question.
We're going to go take a couple of questions from our chat, and then we'll go to the red microphone. So let's hear from our online viewers.
Our first question comes from Joel Bowman in Alexandria, Virginia, who is a member. What materials make up stardust?
Oh, well, that kind of goes back to the previous. Do they mean stardust as in what was collected from the comet 81P Wild-2, or do they just mean in general?
Just in general, astronomy talks often include discussions of dust and observation,
Okay.
or stardust, like you mentioned. And I think they're curious about what materials make up that.
No problem, because I do dust for a living. Jamie 2 weeks ago, that's not it. He doesn't do it as much. I should say, by the way, before I forget, SphereX's main survey started on May 2nd, and we've now covered 3% of the sky. Okay, but so what Jamie was talking about 2 weeks ago is actually started for real. My apologies. Since I do dust for a living, mostly what you see in the dust, oxygen, magnesium, silicon, iron, sulfur. Those are the four big rock-forming elements. Besides the oxygen, are magnesium, iron, sulfur, and silicon. They are, if you look at the cosmic abundance or your solar system abundance, 10,000 hydrogens and about 1,000 heliums for every oxygen. There's roughly the same amount of carbon and nitrogen. That's because of the CNO cycle makes a lot of it in stars. And then 1/10 down by about a factor of 10, it comes your magnesium, your silicon, your sulfur, and your iron. Another factor of 10 below that, you get potassium, you did ask, sodium, calcium, and you get some of the other important rock-forming elements. But the big ones are the magnesium and the iron and the silicon and the oxygen.
Thank you.
You're welcome.
We have a second question from Dave Rabinowitz in Corvallis, Oregon, who is a member.
Oh.
How does the distribution of heavier elements at the RW Auriga stars compared to the distribution in our own solar system?
Oh.
And have you seen any evidence of transuranium elements?
Not yet. The short answer is that while I would love to find an atomic emission line of uranium, I haven't seen any good ones in the literature. The reason why the uranium and the potassium and the thorium would be important, like the question you got before, those are the main radioactive elements heating us today in our core. And we would really like to get numbers for them, but I have not seen good ones yet. Another very important line, now that you bring it up, which is not radioactive, is phosphorus. Again, apologies to the audience, or may be helpful. In your bodies, in my body, the most important element that is, if you will, not very abundant is phosphorus. It's what you have in your ATP. It's what you have in your bones. You have it in your DNA.
You have it in your DNA and RNA.
And it is the least abundant of all the major atoms in your body. Phosphorus is a limiting astrobiological atom, and we're always extremely interested in finding its abundance. And I have not found a good line of it yet.
Thank you.
We'll go to the red microphone.
Ciprian Ivanov, member. You briefly mentioned the possibility of an extrasolar debris causing clumping in an area, and noting the difference between the Aurigae system and most others. Could extrasolar debris explain the difference between Aurigae and most systems?
If you remember, I showed you an image of many different T-Tauri systems looked at by ALMA. Most of them look like B. If you're asking me why A has what looks like a very primitive structure, that's actually a very good question. And if you give me a minute, I will answer it. I may have read too much Einstein as a kid, but it's always bothered me that B is messing with A. Why isn't A messing with B? Why doesn't B look like it's energized and rejuvenated? And there is something that breaks the symmetry. I showed you this, and I told you that B orbits A around like this. Well, B's individual disk itself is spinning prograde, is spinning the same way that B orbits around A. A, from what we can measure, is spinning backwards to the B versus A. So that's what breaks the symmetry, is that when B goes by A, B will just get spun up a little bit more. When B goes by A will actually get its dynamical structure destroyed. Things will get slowed down and the orbits will get all screwed up. Things can start raining down on the central star. So we think that's what may be going on, and that's what's causing the different clumping and not clumping, if that helps. So another way to put it, because of this interaction every few thousand years, we think that B is actually destroying the planets that A is trying to form. Very good question.
It's a starry star world now.
It's a tough life out there.
We'll go to the blue microphone.
I'm Michael Haken, member. Fascinating talk, Casey. Thank you. This is peripheral to the topic of your main talk, really, but I was just curious. You said the meteorite you passed around, I think nickel iron was part of the core of a differentiated object that become molten and spherical and differentiated. And you quoted some size, and you said this is about the limit where things have to be this big to become molten and differentiated. Yes. Two-part question. One, could you restate what that size boundary approximately is? And two, is there some lower size range or limit where an object is big enough to become spherical but not molten?
Okay, so that's a really good question. The numbers that I quote when I say a few hundred kilometers are old. That's an old piece of work. I've had people like Don Brownlee argue that it's actually gotten smaller. But let me set the stage and tell you the physics, if you will. So the amount of radioactives in a body is going to go roughly as its volume. So it's going to go as its radius cubed.
Okay.
Its ability to get rid of that heat is going to go as its surface area, radius squared.
Yeah.
So the body's going to get hotter and hotter as it gets bigger and bigger. It's going to, radioactives have a constant decay rate. If you scale the body up by a factor of 10, you've given 1,000 more radioactive materials to decay and give heat, but you've only created the surface area has only gone up by a factor of 100 for it to get rid of it. That's why bigger bodies get hotter in their center. That's just the basics. It's an R cubed R squared law.
Geometry.
So if you go the other way, you can ask yourself, what is the minimum amount of radioactives you need in order to be able to melt water and then rock? And you find out that there's a lower limit. That's why, for example, we don't think comets, which are kilometer-sized things, they're just not big enough. They don't have differentiated cores.
Sure.
We do think they're primitive stuff. Mike works on comets a lot, I know, because we've worked together in the past. So this is where you can sit down and just do a back of the envelope, and I come up with roughly 100 kilometers radius. And it's simply from that just thought is that what is the heat capacity of the average material? How much energy is coming out of your radioactives with it given decay times? And then how much heat can actually concentrate? It also depends on the thermal conductivity.
Okay, but aren't you forgetting about the heat of accretion,
Hold the
the
microphone.
gravitational collapse?
The heat of accretion
which
is
I think is about equivalent to the radioactive decay in Earth, isn't it? Or more.
It depends on the body. For the Earth, if I'm just having this discussion over drinks earlier, I believe that you only about 5 to 10% of the current energy coming out of the core is actually from the original gene's energy of accretion.
Really?
That being said, if you go look at Jupiter, a much bigger body, Jupiter is putting out more energy from accretion, from its gravitational collapse, than it gets from the sun. So there's your R. Remember, Jupiter's about a factor of 10 bigger than our planet.
Yeah.
So there's your R cubed R squared while working again. So it is true that also that in very early Earth, remember I talked about how the Earth was molten through and differentiated?
Yeah.
That was mostly from, as you're pointing out, not from radioactive decay. That was mostly probably from accretional energy.
Yeah. Okay.
So good question.
Okay. Thank you very much.
But again, let's go back.
I've always been wondering. I've been wondering about that for a long time.
Well, go back to our comets. We know comets don't seem to have cores. We've gone there with Rosetta. There's no big crunchy center. And we know that was a few kilometers across. And so that body...
Sure.
And so we know that comets are small and they're not big enough to melt through.
But then there's Ceres, which is presumably differentiated.
So Ceres is pretty darn big. Ceres is the size of Texas.
Yeah.
So Ceres is plenty big enough to differentiate it.
Yeah. Yeah. Okay. Thank you very much.
You're welcome.
Let's go to the red microphone.
Hi, Paul Ritchie, not a member yet. Back to the previous question, something you just mentioned, the fact that there's several million years difference in apparent age and that A is spinning retrograde, is it possible they formed independently and later became gravitationally bound through a capture event or something like that?
It's possible, but it's a good thing we have this. Actually, keep that slide up, please. So let's say you're two different systems and you're floating through space or you have an encounter. In order to get captured, this goes back to angular momentum and energy. These guys are, if they're coming in from infinity and not bound, they're not going to just encounter each other and say, hey, let's dance for the rest of for millions of years. You have to dump some energy and angular momentum in order for them to become bound. There would have to be another object or something that would have to get thrown out. So it's my understanding that they, on the other hand, I will also point out that binaries are actually very common. If you look, you were to take the average star in the sky and you were to ask, is it single or is it a binary or a trinary or a quaternary? The short answer is that the majority of stars are not singletons. Our sun is actually somewhat exceptional. It's like, I think 30 to 35% are singletons and then 2/3, it's 1/3, 2/3, something like that. So binaries or stellar objects are actually very common. I haven't answered your question totally. It's possible that this was a merger, but it doesn't have to be at all. It's very plausible simply that they formed like this in place. And do they have a lot of angular momentum? Yes, they seem to, but they also seem bound. So could this just have been a big spinning molecular cloud that formed two clots rather than one, and they stayed that way? Yes. Hopefully that answers your question.
Oh, yeah, no, I agree.
I think that's probably more likely than there being a third body that got thrown out.
Other questions?
All good questions.
Okay, I guess no more questions. Then before you go, I have to get back to where I was. We have a few presents for you.
Do I get two of these?
A signed copy of the announcement of this lecture, a rosette, which you already have, but I guess you get an extra one,
Emergency backup rosette.
emblazoned on its side with three bars evocative of the symbol for inductance, named the Henry, for the founder of PSW, Joseph Henry, and a copy of volume 17, first edition, of the Bulletin of the Philosophical Society, now known as the PSW Science Bulletin, which brings together a lot of the original founding documents, the first lecture, the first address of Joseph Henry, talking about why it was formed and what its purpose was and why was called the Philosophical Society, and how scientific discourse should take place.
Yes.
And then there are several histories, a list of our Joseph Henry speakers, and other very interesting material that I commend to your leisure time, if you have any. It is signed by me on behalf of all the members.
Thank you.
So we thank you very much.
Thank you. Thank you. Thank you. Can I give one very quick plug?
Yeah.
I spoke about this subject 2 weeks ago at the Smithsonian National History Museum. And I got to see the back rooms, which are awesome. And this is the fourth time I've talked my way into there. I grew up as a kid here, and I fell in love with Smithsonian and science and minerals and gems and meteorites because of that. If you like this talk and you're interested in meteorites, they have a fantastic collection. And the National Meteorite Collection is actually headquartered at Smithsonian. Parts are finds, if are done under federal auspices, I believe they get to curate some of the material that's found. So really, I recommend. And there's a much bigger brother of this same meteorite there, if you want to see it.
Thank you.
Thank you.
Yeah, I don't know that you're going to get a tour of the back room, though.
I am for it, though.
So before we go, very quickly, the 2516th meeting will be on May 30th, and the speaker will be Mark Palmer. He's chair of the Accelerated Science and Technology Department in the Discovery Technologies Directorate at the Brookhaven National Laboratory, and he'll be speaking about the prospect for developing muon colliders, which promise, at least in theory, to provide much higher energy collisions that are available through the Large Hadron Collider. And even then, the successors that are being talked about at considerably less expense and taking up considerably less space. But it would be interesting because the demands on any device that would be able to produce muons and collide them and are pretty considerable, even compared to a large hadron collider. One thing to note about the schedule, that this year's annual Henry Lecture will be at the 2518th meeting on June 27th, and the speaker will be Jason Dworkin, senior scientist for astrobiology and project scientist for the OSIRIS-REx mission at NASA Goddard. He'll be speaking on analyzing samples of Bennu that have been brought back to Earth by the OSIRIS-REx mission. Mark your calendars so you don't miss this. It is our closing gala event of the season. Please note that PSW members receive invitations about 10 days in advance of each lecture. So be on the lookout. If you're on the friends list, you'll get an announcement of the talk about the same time as well. This is the rest of the season and the beginning of the the fall series. Please check the PSW website often for updates as we complete the fall schedule. With that, let's thank our crew. So thank you very much. With that, I will entertain a motion to adjourn the meeting. And a second, and all members in favor? All members opposed? The meeting is adjourned.